for that.
Okay, let's begin.
All right.
So today I'm going to talk about bus fitting and exact diagonalization. So basically, when we do need the bus fitting, when we how is this? When we need to work with impurity Anderson model. So in this model, as you all know, this model very much. So you have 4 terms. The first term, first 2 terms correspond to impurity itself. So it's impurity energies and interaction between impurity orbitals. And then we have 2 terms here. The first one is the energy levels of the bus, and these electrons are non-interacting. And then we have this coupling term between the impurity orbitals and the bus orbitals. And the problem with doing this, studying this model with exact diagonalization, is that these last 2 terms technically should be the sum should be infinite. So it's a continuous bus of the electrons, and therefore we need. So if you want to do exact diagonalization for that model, we need to discretize it so it will be finite. But the question is how to choose this epsilon k and vk in a sense that we more or less can capture the physics of the particular parameters. And usually we have 2 options. So we can either be in a diagonal basis. So you can see this figure on the left. So you have green is the impurity orbitals and blue is the bus orbitals. And you see if each impurity orbital only coupled to its own bus orbitals, so we call this a diagonal hybridization. And this case is much easier. So in this case, what we can do, we can take each impurity orbital individually and perform this bus fitting for each impurity orbital separately. On the other hand, if we in the basis where each bus orbital coupled to every other impurity orbitals, so this is off-diagonal hybridization, and in this particular case, we cannot do minimization individually because the coupling parameter basically has cross
Sergei, you're talking about minimization, but you haven't introduced minimization problem that you're looking at. Are you going to do that?
I will introduce that problem in some way. Yeah. So basically,
but then let's do that when you come.
Yeah. So basically, we have 2 different type of bus fitting. So basically, one is when the hybridization function is diagonal basis, in diagonal basis, and when it's not. So these 2 problems similar, but computationally the left is much more stable, and the problem on the right is usually super unstable. And if it's possible to avoid this, you should avoid this. And for more detail, you can read this paper by Lipsch and Ishida from 2012, actually. Yeah. So they discussed about the this bus fitting for the DMFT problem and multi-orbital DMFT problem. So to do a bus fitting, we usually have 2 options. Actually, yeah, 2 options. So first option is we do the bus fitting directly in the real frequency. So sometimes we got data from I don't know, from basically LDA, and we have a density of states from LDA, which is formulated in the real frequency, and basically we want to do the minimization of that particular density of state to study the correlated physics from the LDA starting point. And so for that, we introduce the impurity non-interacting impurity Green's function that looks like this, and the hybridization function that looks like this. And then basically we do the fitting problem. So that type of fitting usually works kind of okay if we were able to stay in the diagonal basis. So basically when the hybridization only has its own, each impurity orbital only has its own bus, and this bus does not cross with other impurity orbitals. And
so,
yeah?
Sorry to interrupt you here, but for those of you who are not thinking about this every single day, in this problem, delta ij of omega is a known function. It's an input. It's been provided by LDA or whatever.
Delta not always provided by LDA.
Well, so let's say that the g up here is a known function. And delta is a known function, and now you're finding a fitting function or an approximation to that delta.
Right. Yeah. So basically, what we have, So what we have a function from LDA. Usually, what we have a function on the left side of here, which we don't know exactly how it looks like. So because it has like too many sort of like these bus levels and so on. And we try to fit it with the function on the right, basically. And we need to try the parameters for h0 and for delta, so these two functions basically correspond to each other. Yeah.
H0 is
so h0, sometimes you don't know h0.
So in the usual setup, the equation on the top is an exact equation. The left part here of the delta ij of omega is, what you know out of just basically doing the algebra of the top line. And the right part would be an exact equation if k went up to infinity. But if you only have a finite number of k's, in this case a finite number of fast levels available, then there's an approximation there. Basically, the question then is, how can you choose your VIK and your VDAG kj and your epsilon k's in such a way that you approximate the continuous function on the left most precisely?
Yes.
That's your fitting problem, right?
Yes, that's the fitting problem.
And so the way that you've written it here, it's sort of assumed that these equations are exact, which would be the case if k went up to infinity.
Well, here it's exact equation. It's not a fitting problem yet because you don't have any limits on this sum. So that's basically what we have. So we have non-interacting impurity Green's function, which basically looks like that. And sometimes from LDA, for example, we only have the partial, we only have the density of states, which is the diagonal part of this function. So, it's a diagonal part of this function, and basically inverted part, the imaginary part of minus this thingy divided by pi. And that's, for example, what WASP can give you, or other old LDA packages. Then sometimes you have access to delta directly from some of these LDA packages. They can provide you option how to extract the delta in the real frequencies.
Yeah.
And if you have only the density of states, you can only have this, because this is matrix, this is a matrix, and you cannot simply, if you have only diagonal part, you cannot simply just take 1 over g and say this is your matrix to extract delta. You need to see a delta, because your delta also could be a matrix, and you don't know exactly how this will look.
So in the typical setup, delta that you have on the top line is a matrix with the size of number of orbitals times number of orbitals.
Yeah, same as H0.
Exactly. Then the inverse goes over the entire matrix, and if you want the II component of it, then you do the II component after the inverse.
Yes, exactly. That's what I'm saying. So if you know this function only on the diagonal, you just simply cannot get access to delta directly.
So there's something here that I don't understand.
What?
Why would you know that function only on the diagonal?
Because your output usually is density of states. And the density of states is the diagonal part of G.
Sure, but I mean, if you have a non-interacting, you have just LDA eigenvalues, right? I mean, who stops you from computing what you're doing?
Well, yeah, so you can try, exactly. But sometimes, if you're not too deep into the LDA package that you have, you only have the output, which is your part, your LDOS or PDOS or whatever what LDA gives you. And sometimes you can get access to delta directly, so you don't have you don't need to do any of these tricks with like matrix inversion. Or if you actually have the full access to what you have, you can get delta directly, and then you can a little bit make your life easy, as I will show later.
So in all of the field theory approaches, right, G of omega, or G impurity of omega, is just a continuous function, and it doesn't really have any interpretation in terms of a finite set of impurity states or level states. It's a matrix valued function of real frequency. It's positive semi-definite. It has a positive real part or a negative imaginary part anywhere on the upper half of the complex plane. End of story. And the second line there is something that you never see in the field theory approaches. It's something that you only see in the diagonalization approaches, which is that you take that continuous function and you try to represent it by either a finite or an infinite number of discrete poles.
Because that comes from your Hamiltonian.
Yeah.
So if you take your Hamiltonian and you introduce an action for that Hamiltonian, then you perform Hubbard-Satonovich transformation, you will end up with this function delta.
Right.
That's how this delta and this form of this delta appears.
So the last point there, you're broadening proofs fitting.
Yeah, so the thing is this broadening, because you have infinite number of delta peaks. So if your delta is too small, then you have too many delta peaks, and when you try to minimize this function with shit ton of like sharp delta peaks, you usually cannot do it. Because your minimization will get stuck in the local minimas, and you just cannot move anywhere.
So I think we have to define the problem a little bit better, right? We started out with a delta ij of omega as a continuous matrix value function.
Yes.
We could just look at a continuous scalar function if we assume that everything's diagonal and we take each diagonal part individually.
Yeah.
It's a continuous function. The approach that we see on the right is a fit of a continuous function with a bunch of delta poles. Each pole is located at epsilon k, and each pole is coupled, basically here with a hybridization strength v. So if you're trying to approximate a continuous function with a bunch of discrete delta poles, you're essentially in trouble. That is a bad approximation. What the delta here does is it takes your delta pole and essentially replaces it by a Lorentzian that will make it a little bit easier to mimic a continuous density of state. Right? The little delta in the denominator, the larger you make that little delta, the smoother your Lorentzian, the less spiky your delta pole approximation, and the easier over time you have to represent a continuous function. That's what's going on here.
Yes, and usual choice for this I delta is to be pi over beta, because that what it gives if you have it as a pi over beta and omega equals 0, you have connection to the Matsubara branch.
So I mean
that's what usually people do in the exact diagonalization business.
So if you think a little bit more about this, there's a bunch of energy scales in the problem, and one of those energy scales is temperature, which gives you basically a Fermi function broadening, right? And what that statement says is that you don't want to have features that are sharper than the temperature broadening that you have in your problem anyway. So that essentially means that temperature and that little delta there, which other people call eta, are on the same order of magnitude. And then potential other broadening that comes from other sources can be larger or smaller than this here, and this is a separate problem.
I was under the impression that you wanted to be beta also so that you don't introduce like another scale into the system, which might screw things up.
So that's another good comment. But I think here you're getting into like operational feasibility of being able to actually do a fit that makes sense, versus sort of theoretical analysis of these things. And a lot of, as you'll see, right, a lot of the complications that you have in practice with this approach is that your fits are crap. And you're far outside of the limit where you have a good approximation there. But anyway, sorry.
Yeah. So, and basically for the For the part of the Green's function fitting, that's now we have the minimization problem. So we have the imaginary part of the diagonal Green's function on the left part of the, where is my mouse? Here, on the left part. And then we have this discretized version of this Green's function for the particular orbital. So now you see we have a sum of a like finite number of states. And in addition, you see there is this epsilon has this I index on the top, which means that for each I impurity orbital, we have specific energy for the bath. So it's not now independent from the particular impurity orbital, and we have this fit. And for the hybridization function fitting, it's similar, but we eliminate this epsilon I for the impurity energy. And in first case, we basically have a fit of this set of 3 parameters. Basically, we have epsilon I as an energy of the particular impurity to better resemble the structure of the density of states that we have from LDA. And then we have some finite set of epsilon ik and vik as bath parameters and bath coupling parameters.
So, Sergei,
Yep.
Two comments. So the first is, I've never actually come across Green function fitting as a thing, because the epsilon i's were always given by the local Hamiltonian that, the non-interacting Hamiltonian that we knew. And so does this basically mean that you're changing the non-interacting reference Hamiltonian?
So you can change non-interacting reference Hamiltonian.
And is this a good thing in
So well, sometimes it gives you better fitting.
Okay. So I think that's something where I just have to go.
So if you do not do the DMFT problem, then basically nobody stops you to do that. So this is your low energy model for the for your non-interacting LDA problem.
Yeah. So what you're saying here is that you're changing the non-interacting reference problem to which you're comparing.
A little bit, yeah.
Yeah.
So later on, when you apply to the impurity problem, that epsilon I
Yeah.
will be used as a non-interacting.
What do you mean? The epsilon I will be in your H0.
The new H0.
Yeah.
Okay.
The impurity H0. So your discretized impurity H0.
Yeah.
So nobody stops you to do that. So and if you read this Lipsch,
impurity physics, okay, this is solving a different impurity problem, right?
well, a little bit, but I know,
Yes.
yes. But the thing is, you have basically you anyway solve different impurity problem because your delta is continuous function. And you replace it with the finite number of sets, and well.
So I mean, look, from the point of view of approximating a hybridization function with a different hybridization function that I can actually create in ED, I understand the middle statement there, right? The lower one of your equation. I don't actually understand the top one, but that doesn't mean it's wrong. It just means I have to go read up on what people.
So even if you go to this Lipsch paper, you see that basically what they say is because the deviation from from this epsilon I is usually at some sort of high energy part of G. So that's why you kind of can change it. That's what they claim.
Nervous.
That's what they claim.
Okay. Makes me very nervous. Your top line there really makes me okay. But whatever. The other thing that I want to.
But yeah, the thing is here why you actually do that. That's exactly what I was referring in the beginning. So if you try to fit the G directly and you only have access to the diagonal part of G, you don't know basically you have this inversion part.
Yeah.
And basically you don't have, so you cannot have this epsilon I that you get from the H0, because this is only like a diagonal part of your epsilon of your H0 of your G actually.
So okay, so quick follow-up question: is the Green's function fitting actually used in any of the things we do?
In our case,
Yeah.
we don't use it.
Okay, good.
So
That makes me much happier.
In our problem, we don't use that. So
I think we shouldn't, and you should note the top line there. It has no place in polite company.
Well, so first of all, we don't work in the real frequency fitting. That's the first thing.
But conceptually, I think you're doing a very different problem up there, and I don't see where that problem has any place. But I want to move on.
Yeah.
The tough question here is you have a norm, right? You have a vertical bar on the left and the
Yeah.
right. What is your norm?
Usually it's a least square feet problem. So
Of the wait. Huh?
of this difference.
Of the difference. So well, you have that difference here, and so you want to minimize the square of the integral over
Over
all
the
of
frequency. Yes.
Looking at
Over the
two
some frequency window.
What?
So basically I have omega here, and I have I have take a square for each omega of of this difference, and I do minimization in some frequency window for omega from like minus omega mean to omega max.
So what happens outside of like omega mean and omega max?
So
it's just
usually
zero?
I assume that it's zero. So I basically take the energy window large enough so the Green's function outside of this is basically already decayed to small value.
Okay.
Same basically we have for the hybridization function. So you have also some energy window, and you only care about the minimization within this energy window.
All right, Andre, you had a question.
Yeah, I had a question concerning the Green's function yet again. Sorry for bringing that up. Basically, you have more parameters to fit, so you can also fit more, of course. Is it an advantage, or does it give you more instabilities when it comes to finding the parameters?
So of course it gives you a little bit more instabilities. You have extra parameter to fit.
But you can also fit more things because you have more freedom.
Well, you have more freedoms, but the problem is, so the problem is that extra parameter usually gives you more problem. That's why if you have access to delta, you should use delta.
Okay, so even from technical standpoint, go with delta.
If you have access to delta, you should go with delta. So with G,
Why would you ever not have access to delta?
sometimes you don't.
Really?
Well,
If you know your non-interacting solution and you know your G0 impurity that you want to fit, you just extract the delta. It's just an inversion, right?
well, if you only have a diagonal part of G,
Well, if they only give you diagonal parts.
if you only have a density of states. If you only have a density of states, you don't have access to full G, and not.
Okay. All right, let's move on here.
Yeah. So basically, here an example of the Green's function fitting for the impurity problem. This is LDA spectra for the cobalt atom on the platinum, and basically you have these features for some orbitals. So for the xy, x square minus y square, I would say this fit is kind of okay. The same as for the z square minus r square. For yz, xz, it's kind of shitty, but it is what it is.
So guys, when you look at this,
So the
you can
blue
actually
the
see
blue
the
line
location
corresponds
of the
to the
poles.
fitting.
Right. You can actually see the locations of the individual poles in that thing up there, right?
Actually, no,
Yeah.
not exactly. So these peaks over here, it's not exact location of the pole because your poles are in delta, and it's more or less close to that location, but not exactly.
Okay. Yeah.
Because it's a density of state. You don't have the location of the pole is not exact to what you have in the
Sure. But as a typical case, you see that you get like 2 or 3 features of your function.
Yeah,
Right.
usually you have
And
2 or
if
3
you- If
features.
you took the black line away from this, you would just see 3 Lorentzians.
Yeah.
And that's about the amount, the extent to which you can fit stuff with this technology. Right? You have a function that is very spiky that comes out of LDA or whatever, and you approximate that function with 3 Lorentzians, 2 Lorentzians, something like that.
Yeah. Then if we solve it and compare it to the experimental spectra, it looks kind of okay. So basically we have this blue curve from the exact decomposition, we have black curve from the experiment. You kind of can see that basically the correlations give you renormalization, and the impurity problem can actually capture that renormalization. Then if you do a hybridization function fit, it's a little bit better for you, because then you actually now can put the position of the starting peaks in the precise place where you want them to be. And if basically you put it closer to what it's supposed to be, your minimization problem will struggle much less. And here you actually exactly can see the position of these peaks. So yeah.
And so that's the case that I'm typically, that I'm used to looking at, right? If you look at the black curve and you try to, think how many degrees of freedom you would need to actually describe the black curve, your answer is probably more than 2. And what you see with blue is the best possible approximation that the code could find here to approximate the complicated black one with, 2 peaks and 2 peak locations and 2 pole strength, for the blue curve. So basically 2 features at the right place is what you have as a freedom to approximate.
Yeah, and then you choose this epsilon I in a way that basically you can get proper density from the impurity problem. And then when we compared it to the QMC results, so the position of the main peak is more or less captured by ED versus the QMC. So the small energy features, of course, you cannot get from ED because you have a discretization problem. So that's basically answer to Emmanuel's always question how good or bad the fitting problem is. So, and the answer is it's kind of okay.
I think the answer is very problem dependent, but I think Sergei and I we're from different schools, so we have a difference of opinion here. In my experience, the bad fitting is often a main uncertainty in your problem. It's one of the limiting factors, and it's very hard to get control over it, and it's very hard to improve because just adding more fitting states does not necessarily give you
that's exactly, that not usually helps you, especially if the number of bus states is small. Even adding 1 not usually can help you, because if you look over here, so here I have extra states, so you have 3 peaks, but even with these 3 peaks, you don't capture this low energy sharp peaks here. But
so anyway, it's an approximation, and whenever you're making such an approximation,
you should be aware of what you're doing.
Usually, and you have to be aware that it's very hard to see how bad or how good the approximation really is, short of doing something completely different. And so that's why we often have a couple of impurity solvers that try to solve the same problem. Ideally differently biased ones like, QMC and ED, like Sergei just showed, or, NCA and ED or something like that. I mean, the different methods are then differently biased, and we can understand what comes from the correlation, what comes from the fit.
Yeah, and come on. Okay, and the pros of the real frequency fit is basically you have the real frequency data, you can look into this real frequency data, and you can say, I want to have poles at exact these locations, and it allows you to get the better fit because you actually see where your initial position of your peak is supposed to be, and you can, if you work a lot, you kind of can guess what the hybridization strength should be, what this VIK should be, to actually capture the height of the particular feature you need, and that allows you to get better fit. Also, if you have DFT data, it works better because DFT usually do not give you the Matsubara data. But the problem with this is because you see that you have a lot of sharp features, and here, no, not here, here, yeah, you have a lot of sharp features here, and even if you choose the position of your peak more or less precisely, because you have this sharp feature, you can get into the local minima, and the rest stuff will start fluctuate, and this is something you cannot basically do like without looking into what you get. So you always need to control what you get. That's why it's like really hard to make it automatic. For example, if you want to do like DMFT loop, so the fitting in the real frequency usually horrible in this particular application. That's why in our set we never use that, because we have the Matsubara data, and Matsubara data actually has much better fitting option than you have. So in Matsubara frequency you have a similar problem. So you have the matrix value G that you have as the top line, and from that you can get your hybridization, and the hybridization usually can be written as this continuous function, which you then approximate with the finite number of states, and you have the same, basically almost exactly the same equation you have for the real frequency, except that instead of omega plus I delta, you have this Matsubara frequency I omega n. And here you have options how you minimize the whole problem. So first option is to do minimization of G directly. So you basically, what I mean by G is your target function that you minimize. This like the least square fit problem is G exact minus G fit, and you take a square for each Matsubara frequency you care about, and then you do the fitting. And minimization of the inverse G and basically your target function is 1 over G exact minus 1 over G your like fit function, and you do the least square fit on that problem. Or you can directly do the minimization of your hybridization function, but also what you need to care about, the Matsubara frequency range is infinite, and technically if you have G, basically it decays like 1 over omega, which means that it decays very slowly. But the question is, do you actually need all the data from the high frequency part of your G? And the answer is not always, and for that you can do some different techniques to perform high frequency data suppression.
So
and, yeah?
Because you know the high frequency peak delta, can't you just put the Lagrange multiplier to your epsilons and d's and enforce your fitted delta to have the right high frequency behavior?
The delta is not 1 over omega.
It's not 1 over omega, it's something over omega.
Yeah, it's something, and this something you need to actually fit.
But there's something you can just read off from your high frequency data that you get out of set or whatever.
Well,
right? I mean, we know what it should be.
Yeah, it should be V squared. Yeah.
Well,
it should be V
basically,
squared.
I mean, yes. What you are saying is exactly that the V squared should add up to give the right high frequency behavior.
But the question is because it's the sum, it's the infinite sum of the of these V's.
Well, now it's a sum up to an S. So
yeah,
that's a typical Lagrange multiplier.
Yeah, the problem. Yeah, the problem is you either because you don't have too many of these functions, like these coefficients.
Yeah.
If you do have many of those, yes. So you have basically the sum of these exponentials, and you can actually guarantee the sum rule for the whole function.
But that's not what I'm asking. Even if you have just a few of the V's,
yeah,
by having a Lagrange multiplier that enforces the constraint that the high frequency part goes like the expected high frequency part.
Well,
you have a fitting problem that
yeah, you expected the expected high frequency part of delta goes as basically sum of the V squares,
yeah.
And this is infinite sum of the V squares. So
Well, no, now it's an approximation.
Well, when you do approximation, you have an infinite sum of the v squares that gives you some, let's say, coefficient x, which goes to your high frequency behavior. So you have like x 1 over omega. And on the right hand side, you say you for example have two coefficients. And then you basically saying that you want this v1 square plus v2 square to be equal to x. Yeah. So you have like extra minimization problem. So it's extra constraint. Yes, but the problem is when you guarantee this constraint, it's not always work in a way that your low frequency part will actually be captured correctly.
So it's like you, in a way, it's emphasized on the high frequency.
If you have many of those, yes, you can basically get more of these things, and you then can guarantee the correct high frequency convergence for the delta.
So is what you're saying is
but usually
it's better to compromise on the high frequency data?
Exactly.
Than
because if you look here, so the high frequency data will be suppressed by this data, by omega. Mm-hmm. You have omega in the in the G, you have I omega and you have delta here. So I omega will grow and delta in high frequency will decay. So basically you can, because you need to trade off for something when you do the fitting routine, you would better resemble like proper low frequency behavior of your G than actually like proper high frequency behavior of your delta.
Okay, so the statement here is that I should just not worry about high frequency data because
well, sometimes you need to worry, sometimes you don't.
But it's not something that we just enforce.
So you can enforce it. So we actually enforce it. So we have different type of like enforcement of how you do fitting. So that's why I said that basically when you have this problem, sometimes you need to think about how you deal with your high frequency data, and you can do like suppression. For that, basically what you have this difference, and you have this Wn as a weight function of the basically of your of each Matsubara frequency, and you have some of the Matsubara frequencies from 0 to some fixed fixed m. And if you proper choose the W, you can actually improve your fitting for the low frequency part or for the high frequency part. Depends on how you choose your W. If you're more interested in the high frequency part, you of course will put this to something like, for example, usually 1 will be fine for that. Or you can even add some function of omega that actually force you to focus on the asymptotic behavior. But if you do the fitting of the G, you don't need to care about asymptotic behavior of the G, because asymptotic behavior of the G is 1 over omega. So it's exact known value of this problem.
So it would only be the 1 over omega cube that gets to know about the hybridization. Yes.
Yeah. So, and basically, if you do the inverse G fitting, so you basically have this 1 over G minus 1 over G exact. You have the same weight function, but you can show for the large frequencies so basically when you take this and you go back to this equation, you will see that basically if you really in the diagonal basis and you take this basically 1 over G and 1 over G exact, the only difference you have is you have delta exact and delta that it's approximated delta, and basically I omega and H0 will be cancelled. So basically this fit corresponds to the minimization of the hybridization function. And if you have direct access to hybridization function, you just can do the fit in the hybridization function. And you can see that for the you can show that for the large number of Matsubara frequencies, the difference between this 1 over I omega square times difference between deltas actually approaches the difference between direct Green's functions, not the inverse Green's functions. And basically, if you do the fitting in the delta, you can actually have better asymptotic behavior of the whole problem. And in our set code, we usually do the fitting of the delta. And for the high frequency, like for the weight function, if we have basically the rule, when you get the hybridization function, you look into it, and if you see that basically the delta has the insulating behavior, you set this parameter mean time to 2, which basically tells you that your weight function is omega n. So if you go here, so you will have omega n here, and then difference between like 2 deltas, which ensures that you properly feed the high frequency part. And if you have a metallic behavior of your delta, you set the omega n to 1, or set this mean time to 1, and then basically you just do the minimization of the least square problem for your delta. And we have another option that has, I think it's something like square root of omega as a weight function for the rest. So it basically, it's a trade-off between like high frequency part and low frequency part, and that's basically ensures that you have more or less, you capture the middle part of your hybridization function. And if you need to do the off-diagonal fit, the answer is don't do it. So if you can avoid doing that, don't do it. And because when you have the off-diagonal hybridization, so what you need to do is now, instead of this this set of 2 parameters, you have actually large diagonal matrix of epsilon k and huge matrix for v. And you need to do the minimization simultaneously on a lot of data with a lot of functions, and the uncertainty of that procedure is super big. And then basically, I cannot guarantee that result you will get from the off-diagonal hybridization will actually be reasonable. And in our set code, what we have usually, so we check for the off-diagonal part of delta, and if it's small, we usually say that it's small. And then in your parameters, you can basically choose to only do diagonal hybridization fitting. Another option is you take your delta at several frequencies where delta is a little, like kind of large, and you diagonalize it. And then you rotate your system into that particular basis where delta is diagonal. And then you do the fitting for that particular, in that particular basis, and then you do the transformation back in the into the original basis. And if you do that, the quality of that fit is better than if you will directly do the matrix minimization problem.
But I think the important thing to mention here is that for any one frequency, you can always diagonalize your delta.
Yes,
right? But the fact that you diagonalize it for one frequency doesn't mean that it's going to be diagonal for all the other frequencies.
Yeah, it usually will not. And
Exactly.
in the routines I have for our set code, where I do this diagonalization, I actually check that like the uncertainties for other frequencies, and I print the maxima uncertainty, like maxima deviation from the diagonal in that particular basis.
Yeah, and so there are a couple other things that you need to know here. One is that crystal symmetry just may enforce a diagonal hybridization, in which case you're super lucky.
Yeah, that.
So, cubic systems with like PDG and UG and whatnot.
But yeah, usually if you're not, you can rotate your impurity in a way that your hybridization is diagonal. Yeah. And you can basically rotate it in a way that your interaction will be much more horrible, but that you shouldn't care about, because for ED that doesn't matter anything.
So that